Recording in progress.
Start the recording.
Recording in progress.
Okay. So today I'm covering linear regression. So I'm going to open up the Jupyter Notebook. And this is going to be linear regression with Numpy, of course. So the idea with linear regression is we're trying to fit a line, right? And so, but that's kind of part of the lecture. So we'll talk about that on, we're going to talk about that on Monday, right? And let's just jump into the code. So I'm going to go ahead. So you should, oh yeah, I need to share. So I'm sharing the Jupyter Notebook. Let's go to the desktop here and 365 2022. Let me actually, so let me just create a folder in here. All right. I'm going to go into this folder 2022, and in here I'm going to create a new Python script. Okay, and here we go. So I'm sharing the screen, and our goal will be to fit this algorithm. Okay. So remember, this code is already on GitHub, so I'm mainly modified a little bit, but it'll be pretty much the same one that's already on the GitHub under Machine Learning Foundations. So we are currently under neural nets, and we are going to look at linear regression here. Okay. So, we looked at the perceptron, right? And the idea with the perceptron is actually that in all of neural networks, we're always pretty much reusing a lot of the previous code as much as possible, but we're adding new things, as we go along. Okay. So that's really the objective. So let's go ahead, first of all, and let's think about, let's start with the libraries that we're going to be using. So obviously we're trying to implement everything in Numpy. Okay, so import Numpy as NP. Okay. We're also going to be using sklearn for the data sets. So I'm going to do from sklearn dot model selection. I'm going to import train test split, right? So that module that we used on the perceptron example, I'm also going to import from sklearn the data set. So from sklearn import data sets, and so that we have some data. So I'm actually going to probably just create some random data. This time though, it'll be regression data. Okay, but it'll be the same idea. And we'll plot it or something so that we can take a view of it. So from sklearn import data sets, we're also going to do import Matplotlib. So if I've never introduced this library, have I talked to you guys about Matplot? Yep. So you've heard of it. Yeah. Matplotlib. We'll make a chart today. It's very nice. Pandas is one that we haven't really talked about as much. Those are two libraries that should be covered in more detail in 265, ITS 265. So if you guys, that's the AI class. Also, there's a visualization class that might cover a little bit of it. But, in this course, I don't really. This is Matplotlib, unfortunately, is one of those things that you just kind of have to pick up on your own. You know what I mean? So we don't have a dedicated class, although knowing pandas and knowing Matplot actually are really valuable. All right, so import Matplotlib dot pyplot as, PLT. Okay, so, we're going to use Matplotlib basically in our example here. We're going to need a couple of things. Obviously, we're going to need the predict function and the fit function, right? Very similar to what we did in the perceptron. So we're going to go back to those. But let's start with the data sets here. So I usually put the functions like in this section, and then I have the data kind of after. So where I would have like the main, the main function calls. So let's generate our data set. In this case, we're going to generate some regression data. So I'm going to say data sets dot make regression. And so it's going to be n samples equal, let's say 100 samples. And this will just have one feature, okay? So it'll be a regression of just one thing. So for instance, imagine the formula, you want to know the price of a house. What's one variable that you use to determine the house of go ahead. Huh? Yeah, the square footage, right? So square footage. So think of it that way. Okay, that's kind of the equation for regression that we're doing here. All right, so I'll say like price is equal to square footage times the weight, right? So we're going to have a weight that determines the importance, and this is square of feet, right? And plus the bias. Okay, so that's that's linear regression. That's actually the function for a line, right? Straight line that you learn in high school. And again, we're looking at it, right? So, it never goes away. All right, so, data sets make regression. We're going to do n samples here. I'm only going to do one feature, although we could have more features, right? Like also beyond square footage, we could say, number of bedrooms, number of bathrooms, right? Etc. So features here. And features. And this, we're just going to mark to be equal to 1. So 1x. We're going to add some noise. And what that means is that, we're going to create data, but it shouldn't be perfect. It's a regression, right? And we want to add a certain degree of noise in the samples. So let's say about 20. And then we have random state. And that's just so that the data can be replicated every time, right? So remember, that's the idea with the seed value. And then once we have our data set here, we're just going to do the split because we're going to do the training and the testing, right? So we're going to see how the model performs for a regression problem. Remember that in a regression problem, we are not predicting classes, right? Instead, we are predicting what? We are predicting values, like the price of a house. So we are actually trying to say, oh, this house should cost 150,000 or 190,000 or 350,000, whatever it is, right? So that's what we're trying to predict. So that a regression is different from classification in that we don't have labels. Okay. Let's go ahead here. So we have X train, X test, Y train, and Y test. All right, so we have our variables, and then we're going to do a train test split. Right, so we do train test split with the inputs X comma Y, right? And we're going to say, the test size is going to be equal to 0.2. Okay, so 20% of the data is going to be for testing. And once again, we have a random state. And that's just going to be equal to some value 1, 2, 3. Again, the idea is every time we plug in that specific value, we always get the same results. So now that we have our data, we can take a look at it. Just kind of get a feel for it so that, remember a lot of it is just looking at the data itself. So we're going to do print statement here. X. So we're going to do for X, let's print. We can print the whole thing, actually. There's no reason why we can't do that. Because it's kind of a small data set. And then for the labels, or for the values, we're going to print Y. Okay, so let's go ahead and run this one. I'm going to save this Jupyter notebook. I'm going to actually, let me change the name. So I'm going to say linear regression 2022. Rename it. Okay, and I'm going to regression. All right, here we go. So now I'm going to go ahead and run this. And there we go. So you can see the Matplotlib library does not give me an error. When you guys do this, do you get also the output? No errors? Okay, great. So that's important because, that's to make sure that Matplot is installed. Matplot can be a little bit tricky sometimes. Depends, you kind of get lucky with, with whether when it was installed with the right version or not. Okay. So this is basically the data. Look at it. These are the X values, 100 of them. And then these are the Y values, and there's 100 of them as well. Okay. So these are the values that were generated for the regression. And you can see they're all over the place. And, so it is what it is. All right. So I'm going to go ahead and kind of take this out. Okay. The next thing we want to do is how about we view the data, right? So we're going to view this linear regression data. So I'm going to go here and I'm actually going to try to plot this data. So I'm going to create a figure using PLT, which is from Matplotlib, right? As PLT. So I'm going to use the PLT dot figure. And we're going to define for figure, we're going to define the figure size. So I'm going to say fig size, and this is going to be of size 8,6. So you can play with these values to see different sizes. Now I'm going to do plt.scatter, and this just means that I'm going to print out all the points as a scatter plot. Okay, so I'm going to go ahead here in scatter then. And I'm going to grab because of the dimensions of this, the way it was done, we're just going to slice it a little bit differently. So I'm going to say X, all samples, comma, column 0. Okay. Okay, so this is the data that we have. If we had a matrix that had more dimensions, that had more features, remember, we would not be able to plot it. Okay, if we had like 4 features, etc., we would not be able to plot it like this because that data would be in higher dimensional spaces. Maybe if we had like 1 more dimension, we could do a 3D plot, but otherwise we can't, right? We wouldn't be able. So that's one of the reasons why we only picked 1 feature for this so that it can be easily plotted. So we wouldn't be able to do it. So PLT scatter, that's so here we grab, but basically we just have 1 column, and then we have all the rows. So that's for the X values that we're going to plot. And then we just plug in the corresponding Y values that we're going to plot. We're going to say that the color should be, let's say, let's try color blue. Okay, the marker is going to be zeros or O's or circles. So marker is going to be, I think the little O is like a circle. And then, yes, let's just do that for now. All right, and then over here, let's do plt.plot. Oh, no, that's not plot, sorry, show. All right, and hopefully if we did this correctly, it should, basically show us the scatter plot. So let's go ahead. I'm going to save this and then I'm going to run it. And there it is. You guys see that? So that is the data basically that we just generated automatically. All right, we've got all our samples there, and that's our data. Now we need to build a model that fits this data well, right? And to do that, we're going to have to train the model with the principles of linear regression. Does this make sense? Any questions? Did you guys get this graph? Yep. All right, good. So now that we have this graph, let's go ahead and do the next part of the process. So we plotted the line or the data, the scatter plot. Now we need to think about training. So we're going to do pretty much what we did on Monday for the perceptron. We think of weights as the parameters. So we've got weights and bias, right? And we're going to call a fit function. All right, so fit takes as input X train and Y train. Okay, so it takes X train and Y train. And then we're going to call a predict function. So predict. And predict is going to give us the Y pred. Right, so we're going to predict Y pred given the predict function. The inputs to the predict function will be, of course, the X test data plus the parameters that we just learned from the train or from the fit function. So that's going to be your weights, and that's going to be your bias, all right, which are the parameters in this original equation. So we have to learn B and we have to learn W. Okay, so those are the parameters that we have to learn in our example. So then we're going to go ahead, and once we have this, we can proceed to start thinking about it. Let's start with predict, actually. So let's start with the predict function, as this might be, it's the easiest one. So we're going to do define predict. This is almost the same one that we had on Monday for the perceptron, except it doesn't have an activation function, right? Because we are not mapping this to zeros and ones. We're only keeping the values as is. So it's even simpler. So predict will take X, comma, it'll take the weights as well, and it'll take the bias. Okay, so it'll take the weights, the bias, and X. And so we're going to do Y pred, right? And again, we use conveniently the dot product function. Okay, so we're just going to do np dot. If you remember, this is something that we discussed on Monday. The inputs are x. Remember, we can multiply here the x vector times the weights vector to get the value. We can also provide a matrix of multiple samples, and every row, which is an independent vector, gets multiplied times the weight. And now we have a vector of values, right, for every single test sample. You guys see that? Any questions about that concept? Nope. All right, so we do this times the weights. Okay, and then we're just going to add the bias, the other parameter. And remember here, the difference is no activation function, so we directly return just y-pred, the predicted values. And that's basically it as far as the predict function. All right, so we define here our predict function. Okay, now the next step is we're going to define the fit function. So I'm going to go here and I'm just going to do define predict. Okay, so we've got our predict function. And this is, of course, the one that's a little bit more complex for our purposes. Okay, so we have in the, oh, sorry, did I write predict? I meant fit. So the fit function, right? This is where the training is going to happen. Training happens here. All right, so let's just go into the fit function. So the fit function takes X train and Y train. So let's just call it X and Y. Okay, and just to keep it short. And now we're going to basically define the loop, just like we did before, the number of iterations or number of epochs that we want to define for this. Okay. So what do we need to define? We need the learning rate. So let's just say LR. Remember, this value is really important. So in this case, I'm using 001. Okay, for the learning rate, we're going to do n epochs equal so n epochs is going to be equal to, let's say, 1,000, similar to what we did before. And we want to get the shapes, right? The number, we want to get the number of samples and the number of features. So I'm going to do n samples, comma, and n features like that. So I'm going to just get those values from the X shape matrix, right? So X number of samples is 100 or 80 in this case for the training set, and number of features is 1 because we only have 1 feature. All right, now that we have this one, we are going to initialize the weights matrix. So we're just going to use NP zeros. Okay. And it's going to be, we only need 1 weight because we only have 1 feature. So it's going to be N features. N features. Okay. And then the bias, we can, it'll just be 1 variable as well. So we can just initialize it to 0. So again, the point of this algorithm is not that it should help us to solve every problem, right? Instead, that we should be able to understand the algorithm itself. So now we go to the main loop where we have to do the basic update rules. Okay, so we're going to say for Underscore, it just means we disregard the value in range and epochs. Okay, so we're gonna do, the number of epochs is about 1,000, and we're gonna iterate 1,000 times through the data. And now we need to figure out what we're going to do. So remember that the process was you define the function. It's got random values in it or zeros. You start predicting, you get the prediction, you compare it to the real value, and then you update the weights based on that. You remember that's stochastic gradient descent. So we can call it, just here, this is our first kind of like introduction to a simple way of thinking about stochastic gradient descent, right? And this becomes even more sophisticated as we move on, but it's the same idea, okay? Stochastic just means probabilistic, so it's not even that complicated. It just means that, we start with when do we start with probabilities? Here, right? NP zeros, it's zeros, but it could be some values randomly selected. And that's what is kind of implied by that. So, all right. So now let's predict with the function, even though the function will just give us, garbage in, garbage out. We don't have the predictions. We still want to predict. And every iteration, we want to improve on the weights until we finally have a working set of weights and biases, so the parameters. So in this case, we take X, the test data, we do a dot product with the weights, plus the bias. Remember, this is going to give us a matrix of values, of predicted values, and then we just have to compare them to the real values. Right? So that would be the next step. So here we can say we want to compute, we want to compute the let's say the loss, okay? Or in another way of saying is we want to compare Y pred to Y test, right? So we want to compare those, okay? And we will have them because this is the training phase, right? So we have X and Y. So really, Y, when I say Y test, maybe I should just say Y to make sure I reference this, right? And then Y pred will be this. So I'm going to compare those two and do the updates based on that. Compare Y pred minus Y and update the weights and biases. Okay, so that's the overall basic idea. Okay. So before we do that, let's think about what we're going to need to have. So here, the next step is the update. Is to update the parameters using the gradient. So this is the gradients. Let's call these, just so we have, these are the gradients. And then down here, we do update the parameters using the gradient. So what we got from the previous section, we're going to use in this section. Okay, so the updates are very similar to what we did before. Okay, so we've got the weights. Oops, not there. We've got the weights. And we've got the bias. Yeah, I called this B. It should be bias, by the way. We've got the bias. And so these are going to be updated by just taking the current value of the weights minus the learning rate times the value that we're going to calculate in the previous one. So let's call it DW. We're going to call this DW here. That's one of the values. So that's the gradient that we're going to use down here to update the weights. Let's save that. Okay, and then for the bias, we kind of do the same thing. We're going to take the bias minus the learning rate times, but this time dB, which will be the gradient for the bias that we're going to calculate up here. You guys see that? And then once we have these values, once we've finished the for loop and we've done the training, then we can just go ahead and return the weights and the bias. So we return both of those values, weights and bias, and that's what we use in the predict function. Okay. So really, all that remains in this whole process is for us to compute the DW and the DB. So we want to minimize that loss. So we have to think a little bit about this one. So this is based on, as I said, Y pred and Y, right? Because we predict this value and we have the real value. So we have to, it builds around that. So let's start there. So Y pred minus Y. Okay. Now we are going to give it several samples. So we're giving it a matrix. So it should take the difference for all. So I'm trying to think here. In the if we look at the perceptron, let's think a little bit about in the perceptron code. Oh, sorry, I was looking at my own. Let's go GitHub code. Share that, yeah. In the perceptron, we would take the difference, multiply it times the learning rate. That was the update rule. And then we would multiply the update rule times the X, and that would adjust the weights. So we would multiply this, P dot, activation function, take the difference times the learning rate plus an update and update the weights, right? That's exactly what we did. So here I'm trying to think of something similar. All right, so let's do bias first. I think that one's simpler. So if I do bias, that should be y pred minus y. And then that should give me set of samples. So I'm going to take np dot sum of that, right? I sum these. So I take the differences, sum them. Okay. And I can do I keep getting confused here. I'm doing training. So training is, let's say, 80 samples. All right, so let's see. So there are 100 samples. I do the split on 20. So train has 80 samples. So when I call fit, I call it an X train, Y train. So there are 80 samples, okay, in X and Y. So this is going to have 80 times the weights. It's going to give me 80 Y preds. So then I take the 80 Y preds and the 80 Ys, take the difference of that, do the sum of that. That should give me one value. And then I'm just going to do multiply this kind of to normalize it, 1 divided by n samples. Okay? Because I'm summing it. If I did the mean of this, I would not have to do that. All right, so because I'm summing these, y pred minus y, there's 80 of them. Let's think of this. There's y pred, it predicts 50 minus 40, that's 10, sums all of them, and then it divides by the number of samples. That's an average, basically. So I think we could have just done this with mean, simply. And that gives us the value for the bias. So then we need here for DW. Now this is the more complicated one. We still have Y pred and Y, 80. We do a dot product of those 80 values with the original 80 values, and we should get one value. So let me do NP dot of X dot transpose. Okay, so I think that'll do it. All right, so now we have NP dot, and then the same thing. There will be 80 values in there, so we take the mean. Yeah. All right, so one divided by n samples. Okay. So that should compute the gradients. And now we have the weights and the bias, and we're going to do the update. So that's the fit function. We have the predict function. Okay, so now let's run this code. I think it'll run. Let's see. Okay. Looks like it did run. All right, so now we have Y pred values. So let's plot this again, but let's plot it with the line itself. Okay, so I'm gonna do I'm gonna have to copy this code here. Copy that code so that I have that the original scatter, but now I'm going to put in the plot for the line. So I'm going to do PLT plot. I'm going to use the so let's see, how do I plot this line? So I'm gonna actually need okay, yeah. So we predicted here in next test, we predicted Y pred for the X test. But if we want to plot the line in this original one, we need the original points, right? So we would need the original points there. So let me see. I'm gonna predict, given the model, Y pred line. So I'm gonna call this Y pred line. That's gonna be using predict function, but this time instead of X test, I'm going to run all the data, the original data. So that's when we did the split here, right? We did it on X. So I want to plot all the points. So I'm going to plug in here X itself. Yeah, so that should. All right, and then the predicted values are going to be Y pred line. Okay, Y pred line. And then for this one, then this should plot the line that fits the data. So I'm going to do color for the line equal black. And line width equal 2. And label for this, no label. All right, so then I have Y pred line. So then now to plot it, wait, hold on. So sorry, that's not what I meant to put in. Here should be X, Y pred line, and the weights. Sorry, weights here, and the bottom. I was thinking of the plot. Down here in the plot is where we put that. So X, Y pred line. And now we specify the color, black, and also the line width, which is going to be 2. And just let's try that. So I'm going to go ahead and run this. Gives me an error, doesn't like it. Y pred line is not defined. Define here, Y pred line, this is the exact thing, right? No typos. Let me try this from the beginning. Huh.
Is it because you're using it as a parameter and you haven't initialized it yet?
Yes, this one, right? Yeah, yeah. Okay, this should have been just y. Oh, that's right, nothing. Yeah, because we're predicting. Yeah, sorry. All right, great, good catch. All right, so now try it again. There it is. It's not great, but it's something. What do you think we could try? Do you see that the line is not great? It's not a great fit, right? What do you get? What would you guys recommend that we should try? How about we increment the number of epochs to 2000? I'm not saying that it's going to work, but more training, right? If you're a boxer, train more. Yeah, go ahead. Yours is pretty accurate. Ah, nice. So I like this, right? So this is what you should do. So let's try my idea, and then maybe Noah's idea will be better, right? So, but let's try this one. So let's go ahead. I'm gonna save in here. Just run. What do you think happened to the line with more runs? A little bit better? A little bit. Let's try 3,000. Or actually 4,000. Almost perfect, right? But it's taking 4,000 iterations. So another approach is, let's try Noah's approach. I'm going to reset this to 1,000. What did you say? Just remove one of the zeros? Yeah. So this is another approach, the learning rate, right? So, let's see how it learns. So it kind of makes sense that 0.001 meant very tiny steps. Try to get home, walking like this, it's going to take a long time, right? But if you take bigger steps, you'll get home faster. Yeah. So that's it kind of makes sense that, this should work also. So let's try it. And this is also accurate, right? Given the rate. Does this make sense? Yeah. All clear? All right, good. So this is an approach to take. Now let's try to take this a step further, and I'm going to create, we know it works. So that's it. That's linear regression. Now what I'm going to do is I'm going to try to take a slightly different approach with creating a fit function number 2. Okay. And we're going to try fit2 to see how it works. This is important because it motivates something that we'll be doing as we move on. I'm going to introduce a new function called the loss function. All right, so I'm going to do here. I just copied the function, right? I'm going to call it fit2. All right, and it's similar. So I'm going to do, yeah. So I'm going to do here. So a lot of things are the same. In fit2, we still get X and Y, which is the train data, X train and Y train. I think I was getting myself really confused because I didn't do this. And I wanna avoid that confusion this time, right? So I kept thinking for whatever reason that I was looking at the test set and it didn't make sense. But okay, so then I'm just changing. This is just for my own. So this is X train. And here, this would be X train. this was X train. Like that. Yeah. So it's very similar, but in the perceptron, we did something a little bit different, which this is more efficient because we're doing matrix multiplications and it's just, but since the code is pretty simple, we can actually just do it in a more less efficient but more intuitive way. All right, so I want to kind of make it look like what we did with the perceptron. So I'm going to take that approach now. So in the perceptron, we didn't just give it the whole matrix. In fact, we enumerate it through the X train, right? So that's what I'm going to do here. It's just another approach. So I'm going to do in fit2, yeah. Let's see, I have the learning rates. We're going to set the learning rate to what Noah suggested, 0.01. We're going to have our n samples or n features. Those are set. We have the NP zeros. That's already initialized, the weights and the bias. Okay. And we don't have to do anything else really. So now, instead of just having one for loop, we're going to have two for loops. You always really have two for loops because the way that I did it before, where I only had one for loop, I did the epochs and nothing else, right? The for loop for the epochs, and then I just gave the whole matrix to the model. This worked here because we only had 80 samples. But when you're working with real data sets, you'll have 1 million or so. You'll never be able to give it, about 2.5 terabytes of data, right? You guys see that? So in essence, you always have two for loops. And what you do in this second for loop is you grab the data in batches. So what that means is even if you have 2.5 terabytes, you just grab a whole chunk and you give it of data. Here, I'm going to give it one, but the idea is, two for loops is kind of the way to go. So I'm going to do for, the same thing I did in the perceptron, IDX, XI, and this takes care of, slicing the data out one by one in enumerate. Okay, and then of course, this is going to be from X train. We grab every single sample, and then now we're going to compare on a per sample basis. Okay, so I'm going to do X train. So that should be done. Then here in the next step is to do the dot product. So I'm going to do the dot product, but not between the whole data, and instead just with XI, right? One at a time. So XI times the weights dot product plus the bias, and that is the predicted, right? Initially, those values are random, so they're not great, but I get the Y pred. Now in the perceptron, we did an activation function. Remember, we don't have that here, so that's not required. Now the update should be the exact same thing as the perceptron as well. So really, the difference is going to come in this code segment. I'm going to mark it even with like lines. This is where it varies for us, okay? Right? And in the update to parameters using the gradients, we're just going to say weights are weights. And what we did before was, yeah, the DWs times the learning rate and multiplied it times the X itself. So we should be able to do that. Yeah, let's do that. So what I'm going to do here is I'm going to modify it. It's kind of the same thing, or it should be at least. So I'm going to do update. But this, I'm still going to use the notation DW times XI. Okay. And then here, the bias is going to be bias plus dB times oh yeah, so just plus dB. So that's the way it should work, right? So then now here, dB, because I'm doing this on a per sample basis, right? I'm doing this on a per sample basis. I'm going to take the y pred minus y idx, right? And I take the difference between those two. And I don't need to sum anymore because it's only one value. Times the learning rate. Times the learning rate, which is LR, right? So that should give us DW. All right, and then for this one, it's going to be learning rate times y pred minus y idx. Okay. So this is a little bit more similar to what we did in the perceptron. We take every single sample in the train set, we run it to the y pred function, we take the difference between that y pred and the real one, we multiply that times the learning rate, and then down here we multiply it times the x values and update the weights. Okay. So let's try this approach. I'm not sure if it'll work, but so where do we need to change it? So we need to do fit to. So we're gonna have, let's clear it. Get rid of this. All right, so here we have the libraries. We create the data. Okay, we plot it. We have the predict function here basically. And we have the fit1 and fit2 functions. So here we have to use fit2 to create the weights and the biases and then use them. So I'm going to go ahead and do that. There's an error. Oh, that's right. Yeah. That's right. Good catch. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. So hopefully this will work now. Save it, run. And then let's try this. So this is a Numpy array. Xi should be a Numpy array too. Let's see if overflow encounter and add. Not sure what that error is. I've never seen it before. So that went away, but it's not liking it. So that one's not working. Fit 2. Fit 1 worked, right? But fit 2 just not liking it. Let me see if I can figure out what this means.
When I print out the waste, it looks like there's underneath. When I walk right under the white print.
They get really small. Each of the 39. Man, Noah, that's a very good catch there. No. That's I like that. That's a good, really good catch. Yeah, see here, it comes from calculating with the infinity. So like what you were saying, so the error is definitely related to that. So that's probably what's happening. So I'm trying to see then. So the approach, that's why the first approach is probably better because it avoids that. So I'm trying to see here. Fit one takes all the data and just averages it, and then you get a value all at once. Fit two enumerate take the difference times the learning rate. And then the weights and the bias. Well, the kind of the obvious thing to do is to make this learning rate a little bit bigger, right? See if that still remains. Nope, doesn't like it. How about if I square these? That would also make them bigger, right? I'm gonna do square. I'm really just doing one of these. Okay, try it again. That doesn't want to work. Yeah. So let's see, the fit function worked fine. We're basically trying to do this. Help me out here. I'm trying to convert fit one, right? You know, fit one works. I'm just trying to, instead of giving it the whole data set, I wanted to do it one by one. In theory, that should have been fine. What we did here was so let's modify it a little bit. Let's get rid of this fit two, and let's just use these. Okay, so that should be the weights and bias minus the learning rate times DWDB. Because we need that in the next step. So X predict is simply the dot product of the X and the weight. So that should, yeah, I think that should work. So then the problem is literally here. We've got NP dot weights. The way we did DB is we took all 80 predicted white preds, the difference with the real, summed them, and then divided by the number of samples, right? That's a mean, basically, right? The average. So dB then here should be the difference between the sample. Don't do the learning rate here. Just take the difference. Square it. Yeah, and then this one should be the dot product of X and the difference between Y pred divided by the number of samples. So here we did this. So the equivalent of that would be X times Y pred. The XI here. Yeah, that's, I mean, still, it doesn't like it. Let's print these values. Let's see if we can figure out what's going on. So here we would have print Y pred, right? And then print XI. And print Y IDX Y IDX. That's all we need. Let's do input just to kind of slow it down. All right, so you can see xi is a vector actually, 0.87, y pred is 0, and the value is minus 126. Then y pred is 3509. The value is 13, and the real one is 50. So that makes sense. I don't get why it doesn't. Okay. Let's try again. So the values are pretty large, 13,000 and 15,000. Oh, they're getting really large. You see that? Okay. Oh, but now they got, oh no, this one's pretty big still. And this one is pretty tiny. You see that? Okay. So that actually, minus 19 and plus 19. Do you guys see that? Huh? Yeah, yeah. So you can definitely, so this is actually nice. Something I didn't mean for this to happen, but this is one important thing about what can happen with stochastic gradient descents. You see the numbers can get out of control. So I obviously have some kind of messed up thing in here. Look, plus 36 minus 36. That's where the error is coming from. Plus 70. Oh, they're getting plus 139. Do you see that? All right, so ridiculous. Yeah. So there's definitely something in my, so I think that makes sense, right? That would make it very unstable as a machine learning algorithm. And a lot of people spend a lot of time avoiding these errors. So where is the problem? DW and DB are the ones that are exponentially just exploding. But why? All I'm doing is I'm taking a difference between two values, looking at fit2, taking the difference between two values. I squared it just to get rid of the negatives, really. I didn't think that would be a problem. But that's really where it's happening, isn't it? It's y-pred. Y-pred was 0, then it was, it's predicting increasingly large numbers. Whether positive or negative, they're getting really big. So the weights, yeah, weights are seriously jumping. That wasn't the intention. Let me try something else. I want to get rid of these squares. I'm going to move these functions out of the for loop. Fit 2. And I'm going to just here do, get rid of this. Well, actually, I want to leave this. So this should be, oh, this should, I think this should be a dot product. Okay. I'm gonna do, let's just do this. All right, I'm gonna try this. Okay. All right, so let's take a look here. Once again, and okay. All right, so it definitely didn't like that division. What's happening now? It's are they becoming incredibly large? What do you guys think? The values are changing, right? And they're not becoming incredibly large anymore. All right, so let's see, I'm somewhere like here. Let's say here. So y pred is minus 277, xi is whatever that was. IDX is minus 29, and the DW and the DB. Now DW should not be an array at this point. It should only be a value. So I'm gonna need to extract that. But at least the numbers don't seem to be crazy anymore, right? At least, huh? They're more reasonable, yes. So let's do. So I'm going to remove the input and just see what happens. Okay. The input is here. Yeah, I'm going to get rid of this input. All right, let's see what happens now. Let's go to the beginning. Using fit2, it generated the data there for 1,000 values. Okay. It'll finish eventually. And that's still going. We're in class. Still going. So maybe we should remove. What do the values look like? At least they're not getting out of hand. So that's at least. Is it? I don't know. I don't know. We would have to look at what values we got for the fit1 and compare it. I really just want to see if I'm going to have to remove that print because it's taking too long. But at least we got to see the values, right? They didn't seem to be unreasonable. I've done everything exactly as the fit1, except that I'm not dividing by number of samples. But that was just when we had a whole bunch, 80 of them, we summed them and then averaged them. So I don't see that we need to do that. Let me take this, I'm going to comment this out, and then we'll end with this. I mean, we know that fit1 works. We have the video. I just wanted to do another approach to this. So we've got this. So let's just see, we got rid of that. Let's see what the behavior of the function is. Well, it predicted a line. It's just not a good one. So, but it's progress, right? So that, obviously it's, this is an example of an algorithm where all the machinery is there. It's just not learning. What do you guys think? Yeah, fit1 definitely works a lot better. fit2, I was just rewriting it slightly to be a little bit different, and I don't see what I did differently. I know DW is an array here, so I could, but it shouldn't make a difference. Actually, it should not make a difference at all. Weights is just because weights is a vector, this is a vector, so they're both vectors. It did not learn very well. Fit2 got the same parameters. We could try 5,000. This will tell us if it's just a thing of more training or if it's that the function just isn't learning. Yeah, so the function is just not learning. There's something. All right, we'll stop here. Keep looking at it. All right, and hopefully by next Monday, I'll figure it out. I mean, otherwise we have fit one. All right, so we'll stop here for today. Again, don't you have a homework for the perceptron? Just use, I think it was MNIST, right? Read it in, and yeah. All right, so I'll see you guys on Tuesday. On Tuesday, or Monday, we'll finish up linear regression, and then start a new topic. All right, so that's it.